Hello and welcome. Today we're diving into one of the biggest detective stories in human history, the quest to find the ultimate building blocks of reality. It's an incredible journey that starts with pure philosophy and ends with us being able to actually see the invisible. So, let's get right into it.
Really, have you ever just stopped and wondered about that? If you could zoom in on your hand, past the skin, past the cells, and just keep zooming in, what would you find at the very, very bottom? That simple but huge question is where our entire story begins.
Now, what's amazing is that the first answers didn't come from a lab. They came from brilliant minds just thinking. Way back around 500 BC, an Indian sage, Maharishi Kanad, suggested that if you keep dividing matter, you'll eventually reach a tiny particle you can't divide anymore, the Parmeneu. And get this, 100 years later, all the way over in Greece, a philosopher named Democritus came up with the exact same idea. He called his particle an atom, which literally means uncuttable.
So to see how we went from a cool idea to a scientific fact, here's a quick look at where we're going. We'll start with those ancient ideas, then jump into the first real laws of chemistry. We'll meet John Dalton, the guy who put it all together. Then we'll get to know the atom itself, see how it builds everything, and wrap up with why these tiny, tiny things matter so much.
All right, so let's start at the very beginning. Our story doesn't kick off with beakers and burners, but with pure curiosity. It was a philosophical dream, a logical puzzle, that thinkers were trying to solve with the power of their minds alone.
And for a long time, I'm talking more than 2,000 years, this idea of an atom was just that, a brilliant idea. It made a lot of sense, but there was just no way to prove it. Science and technology had to play a long game of catch-up with human imagination.
And boy, did they catch up. Let's fast forward to the late 18th century. This is where things get really exciting, because we're moving out of the realm of philosophy and into the lab. Scientists like Antoine Lavoisier started doing careful experiments and began discovering the fundamental rules of how matter actually works.
So Lavoisier figured out the first big rule of chemistry, and it's actually pretty simple when you think about it. He said that in any chemical reaction, you can't just make matter appear or disappear. You end with the exact same amount of stuff you started with. It just gets rearranged into new things.
And he proved this with some really clever, elegant experiments. You just take two chemicals in a sealed bottle and weigh it. Then you tip the bottle, let them mix and react, and then you weigh it again. The result? The weight is exactly the same. Nothing was lost, it just changed form. Okay, that was rule one. The next big clue came from Joseph Proust. He discovered that chemical compounds are kind of like a very strict recipe for a cake. It doesn't matter where you get water or how you make it, the elements inside are always combined in the exact same ratio by mass. Let's take water, for instance. It is always made of 1 part hydrogen to 8 parts oxygen by weight. So if you have 9 grams of pure water, you are guaranteed to find 1 gram of hydrogen and 8 grams of oxygen in it. The same goes for ammonia. That recipe is fixed too. These predictable rules were massive clues that something really fundamental was going on. So now we have these two powerful laws, but the big question was still, why? Why are these the rules? This is where our hero, an English chemist named John Dalton, comes in. He looked at the ancient philosophy and these brand new scientific laws and connected all the dots.
So in 1808, Dalton laid out his theory, and it was a game changer. He brought back that ancient idea of the atom and gave it real scientific power. His theory explained everything perfectly. Why is mass conserved? Well, because chemical reactions just shuffle indestructible atoms around. Why do compounds have fixed ratios? Because atoms combine in simple whole number combinations. Suddenly, it all made sense. This was pretty much the birth of modern chemistry as we know it.
Okay, so Dalton gave us the theory. The atom exists. But what is an atom really? What does it look like? How big is it? Let's zoom right in and try to get a feel for these little guys.
This is such a great way to picture it. You know how a huge anthill is just made up of millions of tiny individual grains of sand? Well, atoms are like that, but for everything. The screen you're looking at, the chair you're on, even you're all just a massive, organized collection of atoms.
And here is the part that is just mind-blowing. Dalton could only imagine atoms, but today we have technology so powerful that we can actually see them. This is not a simulation. This is a real image of the surface of silicon, and every single one of those bumps is an individual atom. That philosophical dream from 2,500 years ago, It's now a reality we can see. So just how small are we talking? Well, the scale is almost impossible to imagine. Look at this. A grain of sand is already tiny for us, right? But a molecule of water is 100,000 times smaller than that. And a single hydrogen atom is even smaller still. The scale is just, wow, completely beyond anything we experience in our daily lives.
So atoms are the basic bricks, but the real magic happens when they start linking up and building things together. Atoms rarely just hang out alone. Let's take a look at how they team up to create the entire world around us. When atoms stick together using chemical bonds, they form something we call a molecule. You can think of a molecule as the smallest possible piece of a substance that still behaves like that substance. It's the smallest bit of water that's still, water.
Now, it would be a huge pain to always write a group of 2 hydrogen atoms bonded to 1 oxygen atom, so chemists came up with a special kind of shorthand, a language to describe molecules. Let's take a look at the most famous one of all, H2O.
It's actually super simple to read. The big letters are the symbols for the elements. H for hydrogen, O for oxygen. The little number at the bottom right, that's called a subscript, tells you how many atoms of that element there are. So H, with a little 2, means 2 hydrogen atoms. And since O doesn't have a number, it just means there's 1. And there you have it, the recipe for 1 molecule of water.
So we've seen that atoms are impossibly small, but their tiny size hides just how important they are. They aren't just a part of our world, they are our world. They're the foundation of literally everything.
This quote just nails it, doesn't it? Every single thing that happens, from a star shining to the simple act of you breathing, to the thoughts firing in your brain right now, it's all just atoms interacting. We can't see them, but they are the unseen architects running the entire show.
So we've gone from an ancient question to Dalton's powerful theory. But let's end with one last thought. What if that whole uncuttable idea wasn't quite right? What if the atom itself is like a tiny solar system, made of even smaller, more fundamental pieces? Well, that's exactly where science took its next giant leap.